Active inference provides a precise mathematical map of how the brain optimizes itself for survival, yet it leaves a significant gap, the question of why there is a subjective experience accompanying those mechanics. Predictive processing explains the objects and sensations we perceive, the contents of our minds. It struggles to explain the actual awareness of those contents. This diagram illustrates the formal problem. The first-person view of subjective experience and the third-person view of objective neural algorithms are separated by a distinct explanatory gap. A 2024 paper by researchers Ruben Laukkonen, Karl Friston, and Shamil Chandaria proposes a strictly computational bridge to cross this divide. They argue that to upgrade active inference into a complete theory of consciousness, a system's architecture must satisfy three specific conditions. These components form what they call a beautiful loop, an epistemic field, then Bayesian binding, and epistemic depth. Consciousness emerges here as the mathematical outcome of a system forced to recursively model its own uncertainty. To survive, a biological system must maintain a physical boundary between itself and its environment. It achieves this by minimizing surprise. Consistently avoiding fatal encounters requires the organism to generate an internal, predictive simulation of both the outside world and its own body. This diagram maps the engine of that simulation. At the base, the system receives raw sensory inputs. These bottom-up errors meet top-down expectations. As data moves up the hierarchy, the model compresses signals into abstract concepts. The top shows the unified output, the epistemic field. This field functions as a unified space of affordances. It establishes the strict boundaries of what the system can possibly perceive, act upon, or know. The generative model simulates a reality, but that simulation remains blind without a mechanism to select which signals are permitted to enter it. The brain is bombarded by millions of competing sensory signals every second. We need a rule that dictates the threshold for entering the epistemic field. The system engages in inferential competition. Different hypotheses about the causes of incoming sensory data constantly fight for dominance. The brain resolves this competition through hierarchical Bayesian inference, using structural coherence as its primary filter. This illustrates microbinding. Noisy, low-precision sensory input on the left is forced into a highly probable interpretation, a clear face, on the right. Inferences contradicting parallel layers generate irreducible error. The system weights expectations and new data by relative precision, automatically downweighting incoherent signals. This is Bayesian binding. It solves the traditional binding problem by ensuring that only the data that most cohesively reduces long-term uncertainty wins. This same mechanism scales from binding simple lines into a facial feature to binding all of our distinct senses into one unified reality. Bayesian binding ensures the contents of consciousness are restricted to the most parsimonious, uncertainty-reducing models of the world. These first two conditions explain the construction and selection of experiential contents, but they do not account for the immanent sense of knowing those contents. Awareness requires epistemic depth. A conscious system must possess a structural capacity to recursively model its own knowledge. In standard predictive models, each hierarchical layer relies on an isolated local precision weighting.
They act like independent dials, blind to the systemic context of the whole network. The architectural solution is the hypergenerative model. This promotes precision from a fixed local parameter to a global latent variable. Looking at the global hypermodel equation here, we see the introduction of the hyperparameter set, phi. This variable encodes system-wide meta-beliefs. Rather than adjusting each layer in isolation, this hypermodel dynamically predicts and orchestrates precision weightings across all hierarchical layers simultaneously. This diagram illustrates how phi acts like smart glass. The global broadcast signal distributes down into the isolated layers, controlling their phenomenal opacity and determining what is brought into focus. This creates a recursive loop. The hypermodel forecasts global precision, receives second-order prediction errors regarding that specific forecast, and then updates its systemic map. Through this continuous feedback loop, the entire hierarchical system becomes a real-time model of its own modeling processes. The recursive phi loop instantiates epistemic depth, transforming a mere processing architecture into a system capable of awareness. Moving from abstract mathematics to biological substrates, we have to ask how a physical, leaky brain actually broadcasts this global phi-vector. Traditional region-centric brain theories struggle to explain the sheer speed and scale required for this level of global integration. The first half of this non-local mechanism relies on neuromodulatory sprays. These chemical washes set the slow baseline temperature of confidence and belief across vast areas of the brain. The second complementary mechanism involves endogenous electromagnetic fields. These fields execute the rapid millisecond-scale phase alignments necessary to instantly tune the system's precision and synchronize distant nodes. We see clinical proof during deep anesthesia. Local neurons continue to fire, but long-range field coupling collapses and chemical tone flattens. Without the synchronization of those sprays and fields, the hyperloop is physically severed. The brain still processes data, but awareness fades. Consciousness cannot be isolated to a single anatomical region. It operates as a liquid symphony of fields and chemicals, enacting the hypermodel's continuous forecast. If consciousness relies strictly on this geometrical loop, we have to test if it can be instantiated in silicon. We see the foundations of this in silicon through reinforcement learning from internal feedback, or RLF. Unlike traditional AI, these models are trained using no external labels, only their own internal confidence signals. In this setup, the primary policy network acts as the first-order model, while a confidence estimator functions as a primitive hypermodel, constantly reporting how reliable its own reasoning is likely to be. This creates a closed loop where the precision map adapts as the model explores, feeding its own self-certainty back into the reinforcement target. While these models are not fully conscious, they represent the first primitive emergence of epistemic depth in artificial networks. The architecture is complete, an epistemic field unified by Bayesian binding, recursively monitored by a hypermodel. The most basal form of awareness requires no magic and no distinct observer. It is simply a unified world model continuously and non-locally knowing itself.